most of what I'm going to talk about probably will be covered in more detail in the workstations. I'm going to just talk a bit about the sort of basics of mechanical ventilation. And so basically for, air to move from the mouth into the lungs, there has to be a pressure gradient. Without a pressure gradient, air won't move from the mouth into the lungs. So essentially, that's the only way you can, overcome the resistance of the airways and overcome the elastance of the lung and then keep the alveoli open. So there are only two ways to ventilate a patient, either negative pressure or positive pressure. Positive pressure, what we generally do when we spontaneously breathe is create a negative pressure because we, inhale and there's a negative pressure created and air moves because at the mouth there is zero and at the pleura there is negative pressure, air moves from the mouth to the alveoli. But other option, of course, is to create a positive pressure at the airway, at the mouth, so that air moves into the alveoli. So there's only negative or positive pressure. And initially, we had to have the negative pressure ventilations, which is so-called iron lungs, where, a negative pressure was created around the chest and air moved. And that was the original ventilators called the iron lungs. But there was an epidemic of polio in Scandinavia in the 50s. And they virtually ran out of, iron lungs, because they were overwhelmed. There was a major epidemic of polio in the 1950s, and that is when positive pressure sort of ventilation became took over. So this is, though Vesalius described positive pressure ventilation several hundred years ago, it was only 400 years later, after this epidemic of polio, when actually positive pressure ventilation became more popular. Because they ran out of negative pressure ventilators, the medical students had to take leave. They closed down all the medical schools. All the medical students had to manually, with an ambu bag, ventilate most of these patients who were suffering from polio epidemic. And that is when positive pressure ventilation first began. Though formally positive pressure ventilation began in the MGH in 1955, and then of course with that, so-called intensive care also developed as a new specialty with the advent of positive pressure ventilation. So for most circumstances nowadays, we have positive pressure ventilation, which basically means that you create a positive pressure at the mouth, so that air moves, because the gradient between the mouth and the lung, and then therefore air moves from the mouth into the lung. That is positive pressure ventilation, which most of us now deal with. So essentially, a mechanical ventilator is a flow generator. So basically, you get there's a oxygen and air are received from either a blender or a cylinder or a wall outlet or whatever. Then, because that air that comes is under pressure, that pressure is reduced. Air pressure is reduced, and then it is mixed with the oxygen to the desired FI2, to the FI2 that you have set. And then once this oxygen and air are mixed, they are stored in a receptacle within the machine. They're just stored there. And then the machine generates and regulates the flow. Actually, what the ventilator does is basically generates and regulates at what rate should the air go into the lung is what is controlled by the ventilation. So essentially, it's just a flow generator. First of all, it reduces the pressure of the air, mixes it with oxygen to the desired FI2, and then delivers it to the lung at a particular rate of flow. That's all it does. That's a flow. So ventilator is essentially a flow generator. So basically, what happens? This flow will continue until a certain limit has been reached. How much the flow should go? How much of air should go into the lung? That is called a certain limit. So this flow of air from the ventilator into the lung will go up to a certain limit is reached, and once that limit is reached, it will continue till the ventilator gets a signal that it has to cycle into expiration. Then it stops. So it doesn't mean that since once the limit is reached, flow stops. The original ventilators were so-called pressure cycle ventilator. It means the moment a certain pressure was reached, they automatically cycle to expiration. But that means the ventilator time was very, very short. Nowadays, even after the limit is reached, it continues till the ventilator gets a signal that it should switch to expirations. Okay? So that is called the flow. Then of course the flow reverses. The inspiratory valve closes and the expiratory valve opens. So initially when there's inspiratory valve opens, so air can move into the lung. Once it gets a signal that inspiration is over, the inspiratory valve closes, the expiratory valves open, and the flow of air reverses back from the lung into the ventilator. And obviously, as we all know, that mechanical breaths may be controlled or assisted. I mean, that is standard, of course. It can be controlled, or control basically means in patients who are completely knocked out or patients who don't have a drive of their own, especially in anesthesia. By and large, in ICU, by and large, we almost never use controlled ventilation except in very, very rare circumstances when the patient is completely sedated or paralyzed. Usually it is assist control, but in surgery, etc., you can have controlled ventilation, which means the patient is not making any spontaneous effort of his own. Okay, so what is the limit? So like I said, limit basically means it could be either flow limited or pressure limited. That means flow limited means once the flow reaches a certain level, that's the rate at which the flow will continue during inspiration. It could be 60 ml per minute or whatever rate you have, 60 ml per second or whatever rate is controlled. That is a flow that you have set. That means the flow is limited, but once the flow is limited, the pressure in the lung will keep varying depending on the compliance and the resistance of the lung. Or you can have pressure limited. Pressure limited basically means that the pressure that has been set. So it could be either flow limited or pressure limited. These are the only two limits that you have in mechanical ventilation. So if this pressure limited, the volume that is delivered to the lung will vary, depending upon again on the compliance and the resistance of the lung. Again, this is, I won't keep saying this again and again. Sometimes you have modes which take advantage of both, which is sort of the best of both worlds. There could be a pressure controlled mode, but the volume is the one that is set. So I'll talk about it. They're called dual modes, where you have both modes. You combine pressure and volume. We'll talk about that in a little more detail. So essentially, this is what happens, that you have a trigger. Trigger basically we'll talk about. Basically, that means the ventilator now gets a signal that it should start delivering a breath. That means once it gets a trigger, once the ventilator is triggered, the inspiratory valve opens and air moves from the ventilator into the lung till the certain limit is reached. That limit could be certain flow or a certain pressure. Once that limit is reached, flow will continue till it gets a signal to cycle to expiration. Once it gets this signal to cycle to expiration, then the inspiratory valve closes, air doesn't go into the lung anymore, the expiratory valve opens, and there's a reversal of flow from the ventilator back into the lung. That is expiration from the lung back into the ventilator. So that is expiration as over till the expiration ends, and then again the next signal is there for inspiration. So basically, then how does the ventilator know that it cycled from inspiration to expiration? That is called the cycling. Basically, how does it cycle from inspiration to expiration? So basically, it could be the time cycled, volume cycled, or flow cycled. Now, time cycle basically happens, of course, commonest is when there is CMV, when the patient is not doing any spontaneous breath at all. It's all controlled ventilation. So suppose you kept a rate of 12 every 5 seconds, the ventilator knows that it has to deliver a breath. If you give a rate of 10 every 6 seconds, that is automatically time cycle. That is the commonest, time cycle. But some other ventilator modes also have time cycle. That means after a certain time, automatically the ventilator knows it has to trigger a breath. Otherwise, you could have what is called volume cycled or what is called flow cycle. We'll talk about that. Volume cycled or flow cycle. So how does it cycle to expiration? It could be one of these three. Time cycled, volume cycled. That means once a certain volume is reached, suppose you kept a volume of 500 or 450 or whatever volume is you have kept. Once that volume is reached, then it cycles to expiration. And sometimes you have what is called flow cycling. Flow cycle means when a certain flow, inspiratory flow is reached, then it cycles to expiration. We'll talk about this in little more detail. These are three ways in which it can cycle to expiration. So we'll talk now about the mode. So whenever you're talking about any mode, basically you're talking about three things. What is the trigger, what is the limit, and what is the method of cycling. If you know these three things, then you can always describe any mode of ventilation. The trigger, the limit, and the method of cycling to expiration. With that thing, you can describe any mode of ventilation. Whatever you might think is very complicated, but it's not really that complicated. And of course, so basically, you also need to know whether assisted or assist control. And basically, the main difference really is that in assisted modes, the patient makes an effort. That means you can make out there is a negative pressure. The patient is making an effort. Whereas in controlled modes, the patient is not making an effort. The ventilator is doing all the work. But like I said, most of the times in ICU, you almost never put them on control mode because then it's more likely to have some kind of diaphragmatic atrophy, etc. So unless for some reason raised ICP or whatever, or in severe status epilepticus or whatever, you need to paralyze them, by and large, you allow assist control. It means you allow the patient to make some effort, by and large. Except in the theater where they have control mode. In the ICUs, by and large, we try and use assist control unless there is some exceptional circumstance. The first mode, the commonest mode really is the volume target ventilation, which all of you know, CMV volume controlled or volume targeted ventilation. So usually it is patient triggered. If it is assist control, most often it is patient triggered. It is patient triggered. The patient trigger could be either volume or it could be either pressure or it could be flow. I'll talk about trigger. So it is patient triggered, flow limited. The limited is flow. The flow is limited. That means if you look at the top, the flow is, it doesn't go above the certain level. Depends upon whatever flow rate you have kept. So this is the flow is limited and it is volume cycle. That means once the volume reaches a certain volume that you have kept, then it cycles to expiration. So volume control ventilation is patient triggered, flow limited and volume cycled. Now flow is easy to say. Suppose you have kept it, ultimately the time is given for each inspiration is 1 second. And you can find ml tidal volume. So it is going to be 50, the rate is going to be, it can be 5 liters per minute. You can calculate so much tidal volume has to be delivered over so much time. So the flow can be calculated because the flow is constant. So it's constant flow. The flow doesn't change. The rate of flow is same. What will change will be the pressure. Okay, but flow is constant. So volume control ventilation is patient triggered, flow limited, and volume cycle. Okay. Any questions? Please ask me. It's not very difficult, but so like I said, in volume control ventilation, the flow will remain constant, the volume will remain constant, but what will change could be the pressure. The pressure delivered at tidal volume might change depending on the resistance and compliance of the airways. If the resistance increases or the compliance decreases, the pressure required to deliver the tidal volume will increase, whereas if the compliance decreases, obviously the pressure required will be changes. So pressure might vary, but the flow and tidal volume are constant in volume cycle ventilation. Okay. So this then is pressure. Then we of course another mode that is used commonly is pressure target ventilation or pressure control ventilation. Again, it is patient triggered, but here the limit is pressure. The pressure doesn't change. So you can see the pressure is constant. The pressure is limited. Okay, the pressure doesn't change. So whatever pressure you kept, 15, 20, 25, that will go on throughout the whole of inspiration. But it is time cycle. So you keep a certain rate and you keep a certain I ratio. Generally, what we do is keep a certain rate. You might keep a rate of say 20. And you keep an I ratio 1:2. When you take 20 and I ratio 1:2, it means each breath is 3 seconds. And when you keep an I ratio 1:2, it means 1 second for inspiration, 2 seconds for expiration. So the ventilator ultimately, remember what you are fixing really is inspiratory time. Expiratory time might vary. So what you are fixing when you are keeping this rate and this I ratio is inspiratory time. So some ventilators give the option of just fixing inspiratory time. Because I ratio will change depending upon the patient's respiratory rate. But inspiratory time remains constant depending on what you have set. So when you have set a rate of 20 and I ratio 1:2, it means the inspiratory time is 1 second. Because now if the patient breathes 30 times a minute, his inspiratory time is still going to remain 1 second. But expiratory time will now come down to 1 second also because each breath is 2 seconds. You understand? So now the I ratio is not 1:2, the I ratio is 1:1. So remember the I ratio that you have set will remain the same only if the patient is breathing at the same rate. If the patient is breathing at a faster rate, the I ratio is going to change. But what will not change is the inspiratory time. The expiratory time will keep changing. The expiratory time will shorten if the patient breathes faster, but the inspiratory time remains 1 second. So essentially, what you are setting with all these things is the inspiratory time. And most of the newer ventilators give you a choice of setting the inspiratory time fixed inspiratory time, 0.8 seconds, 1 second. Generally, most patients are comfortable with inspiratory time of between 0.8 to 1.2 seconds. Generally, that's what the usual inspiratory time should be set. In asthmatic, COPD, sometimes you might keep a shorter inspiratory time, but generally 0.8 to 1.2 seconds is the usual comfortable inspiratory time for most patients on a mechanical ventilator. And so whenever you're calculating I ratio, rate, etc., in your mind you should calculate what is the inspiratory time set for the ventilator, because that is what is going to remain constant. So in pressure control, basically it is patient triggered, pressure limited, and time cycle. Okay, cycle by time, same thing. So every 3 seconds, if you get to a rate of 20, every 3 seconds it will cycle to expiration. So in pressure control ventilation, the pressure remains constant. So the pressure remains constant, but depending on the compliance and resistance of the lung, the tidal volumes will change. Okay. So in pressure control ventilation, pressure is constant, but volume of the lung delivered changes depending on the compliance of the lung. This is basically the same thing I've said, that because compliance is volume of delta pressure, depending on one changes, the other will obviously change. Okay. So then you have something called PRVC, or different ventilators have different modes, but essentially they call, in the MACA exercise, they call pressure regulated volume control. This is supposed to combine both the modes. Okay, you have pressure control kind of delivery, but tidal volumes are fixed. So it's a PRVC, it's a dual control mode. Okay, it's supposed to advantage about pressure. So similarly, when you have pressure support, I'll talk about pressure support, like something called volume support. So basically, it delivers whatever tidal volume that you have set. You have kept tidal volume of 400, 450, whatever. It delivers the tidal volume in a pressure control kind of delivery at the lowest pressure possible. Okay. So how does it do that? Basically, initially it gives what's called a test breath. It gives a test breath of 450 ml. In a volume control breath, it gives test breath of 450. It calculates the compliance of the lung. And by calculating the compliance, it decides this is probably the amount of pressure I need to deliver this tidal volume. So it gives that much pressure. If the patient gets that tidal volume, then the same pressure is continued. But if the patient gets a low tidal volume than what it has been calculated, then the ventilator automatically increase the pressure. If the patient gets a higher tidal volume than what it has calculated, then the ventilator automatically decrease the pressure. So then it keeps doing this every 5 or 6 breaths and decides what is the best pressure to deliver that particular tidal volume. So though the mode of delivery is pressure control delivery, tidal volumes are guaranteed. Normally in pressure control ventilation, depending on the compliance and resistance of the lung, the tidal volumes can change. But in PRVC mode, tidal volume doesn't change because the ventilator automatically adjusts the pressure required to deliver that particular tidal volume. Okay, so PRVC is a good mode in patients who are completely comfortable or reasonably sedated, whose change of mode of whose respiratory rate and frequency are not fluctuating too much. There's not much of fluctuation in their respiratory pattern, because it's ideal in ventilating patients for ARDS. Because on the one hand, you're using a pressure control mode of ventilation, at the same time you're limiting tidal volume. So it's the best of both modes, but it should remember for these PRVC to work really well, the patient should be comfortable, his breathing pattern should not be very fluctuating. It's good in well sedated patients and getting the best of both worlds. It may not be that great in patients whose breathing patterns are not consistent. Then, of course, we have pressure support ventilation. Now, remember, a lot of people tend to think that pressure support ventilation is a weaning mode. It is not a weaning mode. It is another mode of ventilation. Remember this. Everybody thinks that you have to wean, change from whatever control mode or assist control mode, change pressure support. I don't know why. It is just another mode of ventilation. Okay. Weaning can be tried to many modes that they are on. You don't have to change the pressure support to then try and wean. Probably that will be talked about in the afternoon. I won't talk too much about that. But pressure support is another mode of ventilation. Pressure support is more or less the same as pressure control ventilation. Suppose one person is on pressure control ventilation of 15, the other person is on pressure support of 15. If both of them are, the main thing of course in pressure control is the patient need not trigger. In pressure support, the patient has to trigger every breath. That is one thing. The patient has to trigger every breath. But otherwise the pressure delivered is 15 in both. The main thing is how does it cycle to expiration. In pressure control, it is time cycled. In pressure support, this is flow cycled. Means when the patient makes an effort and he gets a pressure of 15, afterwards the flow starts decreasing. Okay, the flow starts decreasing. So once the flow falls to 25% of the peak flow. Once this is the initial flow, it's very fast. Once the flow decreases 25% of the peak flow, then it cycles to expiration. Okay. The default is 25%. That is called the expiratory trigger sensitivity. How does the ventilator know it will cycle to expiration? That is called the ETS, or the expiratory trigger sensitivity. So default in most ventilators is 25%. So once the flow decreases to 25% of the peak flow, the ventilator will cycle to expiration. So pressure support is flow cycled, pressure controlled is time cycled. Otherwise, for all practical purposes, there is no difference. Of course, pressure control can also be without triggering. Pressure support always has to be triggered by the ventilator. Okay. So this is the flow cycling. This is called the expiratory trigger sensitivity. In most patients, it is 75%. But nowadays, most ventilators give you the chance of adjusting the ETS. Some patients may not have a very good effort. They may be having critical neuropathy, diaphragm may be weak, or they may have ARDS where you want to prolong inspiration slightly longer. In that situation, you can decrease the ETS to 20%, 10%, 15%. So therefore, inspiration will be prolonged. Okay, you can decrease it. Conversely, you have patients with COPD, asthma, etc., where you want to keep the effort is that the tidal volumes are good, the effort is pretty good, but you want to decrease inspiration and prolong expiration. There you can keep the ETS at 40, 50, whatever. So you understand? So virtually by manipulating ETS, you can adjust inspiratory time even in pressure support. So for all practical purposes, nowadays, pressure control, pressure support are almost identical if you know how to adjust the inspiratory time. You understand by using ETS. Okay? Do you understand this? And then somebody will talk to you about this in more detail, but this is what. So ETS can help you adjust time in pressure support. Otherwise, default is 25%. Okay? The other important thing is something called rise time. Rise time is basically more in pressure control modes or pressure support modes. Rise time is how quickly the pressure is reached. You kept a pressure of 20. How quickly is the pressure reached? Sometimes, the pressure reached very quickly. The patients are uncomfortable because they get a blast of air very quickly. They find it very uncomfortable. Like in Cpap, you have ramp time. You know how that ramp time is much slower, but similarly something called rise time is how quickly the pressure is reached. Sometimes the patient is flow starved. He's very breathless. He needs the pressure very faster, and if you keep a very low rise time, he feels so. You shouldn't have very slow rise time, nor should you have very faster rise time. So normally you adjust the rise time so that the patient is comfortable. It is not either too fast for you. You can ask the patient, is it too much or too slow? Or you can look at the graphics to tell you whether the rise time is proper or not. So if there's an initial overshoot on the pressure curve, it means that the rise time is too fast. It means you need to slow down the rise time. If it is like this, it means the rise time is too slow. It means the patient is likely to be flow starved. The patient is likely to get air hunger. This is too slow. This is too fast. What should be ideally should be something like this. This is how the rise time should be set, so that the graph looks something like the pressure tracing. You understand? This is how you adjust rise time. It's a matter of patient comfort. It doesn't make a big difference. The only other problem in pressure support, if you keep a rise time that is too fast, because the initial flow is too fast, it will fall to 25% of its peak flow very quickly, because the initial flow is very fast. Therefore, inspiratory time might be too short. So that is another problem you have with too high a rise time in pressure support ventilation. Therefore, that's the other thing you need to take up. These are subtle things that might help you to make the patient, otherwise patient is not comfortable ventilate, everybody sedates paralyzed. That's an idiot's way of ventilating. Anybody can do that. That's what we tend to do. Patient not comfortable, sedate, paralyzed. But that's not, you should use your mind, try and adjust your settings to make the patient comfortable, try and minimize sedation, paralysis, etc. That's how otherwise there's no point. If you had just paralyze everybody, you don't need this whole class. You can just paralyze and go to sleep. Then, of course, another mode that is very popular in the past, fortunately or unfortunately now getting completely out of vogue, intermittent mandatory ventilation. It was supposed to, basically, the premise was that you're giving, the patient is breathing spontaneously, but in between, the ventilator delivers some breaths to so-called support the patient. That was supposed to be the way of the background pure intermittent mandatory ventilation. But actually, suppose the patient is breathing 30 times a minute, it doesn't mean that the brain stops triggering the moment he gets a mandatory breath. The brain can't suddenly stop, the patient gets a mandatory breath, stop triggering. So the brain will continue to trigger 30 times a minute. So the mandatory breaths actually don't really help the brain in giving the brain rest or giving the diaphragm rest. The patient continues to breathe at its own rate. And quite often there is a clash between the patient's own breathing and the ventilator breath. Sometimes there's a clash because the ventilator is delivering a breath, the patient is making a breath. Sometimes the expression of the patient and the inspiration of the ventilator might clash. So IMV was given up because of these problems. Then they had something called synchronized intermittent mandatory ventilation, or SIMV, which still is very, very popular with, especially with anesthetists for some reason. I don't know why, but anyway, it's a very popular mode with most anesthetists run ICU. It's not this. I'm just saying it somehow seems to be very popular, but the whole thing was that they try to, so they said they have this mandatory breaths and they try and synchronize the patient's own breathing with the mandatory breath. So if the patient is not breathing, then he gets the mandatory breaths. But if for some reason the patient makes a breath, they try and synchronize, they try and match the patient's breathing with the mandatory breath. So there is no, clash between the patient's breathing and the ventilator. That is all premise of a SIMB. The problem with SIMB is that when the patient is taking a mandatory breath, for him to breathe, he has to do a lot of work. He has to generate enough effort to open the inspiratory valve to draw the air. So actually SIMB makes the patient do much more work. And several studies have shown that with SIMB, actually weaning gets delayed because patients do much more work, they get much more fatigue. Therefore, nowadays SIMB is not really a great mode. But to overcome this extra work, people are doing SIMB with pressure support. So when he's breathing spontaneously, they don't make him just breathe spontaneously, they give a pressure supported breath so that he can breathe spontaneously and get support to open up the valves. But then people say, why do you want a SIMB pressure support? Just have pressure support. Why are you making life so complicated? Just give him pressure support. So why do we have to make it, so complicated? So actually you have to keep it simple. But still, I'll talk about SIMB because again, a lot of people still tend to use it. I don't know why, but they still tend to use it. Like I told you, several studies have shown that actually SIMB has prolonged the entire weaning process. It's not really recommended. So like I said, in here they have pressure support. So the mandatory breaths are not, the spontaneous breaths are not spontaneous. They are supported with pressure support. Okay. So what basically happens in SIMB is that basically there is, suppose you keep a rate of, 6 SIMB breaths. So there is so every, 10 seconds you get one SIMB, you get a mandatory breath. That is possible. Okay, so this is called the SIMB period. Then for this 7 seconds, the patient can breathe spontaneously. Okay. Now what happens in the SIMB cycle? The first 90%, if the patient makes an effort in the first 90% SIMB cycle, it will synchronize that effort with the SIMB breath, the mandatory breath. If it doesn't make an effort in the first 90%, then it will give a mandatory breath. So this is how the SIMB tries to synchronize the patient's effort with its own breath. Okay, so that there's no clash. During the SIMB period, it waits for the first 90% of the SIMB period. If there is any breath, it is synchronized with the patient. Otherwise, it gets a mandatory breath. So in SIMB, basically there are 3 types of breath. One is the controlled breath, the mandatory breath. One is the assisted breath, the synchronized breath. And finally is the spontaneous breathing, which could be pressure supported. This is the 3 SIMB. So in SIMB, actually the patient is getting 3 types of breathing. All this is really theory, but by and large, like I said, now keep it simple. You really don't need to use SIMB. You can use pressure support, pressure control, volume control. These are all modes that you need to know about a theory for your exams, etc. In actual life, you really don't need all these things. Now, Cpap is another mode again with actually a spontaneous breathing mode. Cpap is a spontaneously breathing mode. The only other thing I want to talk to you about very briefly is that sometimes from a ventilator, you use, ventilators by NIV. So generally, you can use the conventional ventilators or you can use the BiPAP devices. So sometimes you can change from a small ventilator to the bigger ventilator or vice versa. So you should know what is pressure support. Generally, when you're on a ventilator, use pressure support for NIV. So if it is pressure support of somebody's on a PEEP of 5 and a pressure support of 10 on NIV, on the smaller machines it is called IPAP and EPAP. So PEEP is equal to EPAP. So suppose somebody is on a PEEP of 5, EPAP is 5. But IPAP is not the same as pressure support. IPAP is equal to pressure support plus PEEP. So that is the only difference. So suppose somebody is on 10 of pressure support and 5 of PEEP. When you switch him to a BiPAP machine, he has to be an EPAP of 5 and IPAP of 15. Okay, you understand? IPAP is the peak inspiratory, is the total inspiratory pressure, not just pressure support level. That's the main difference. And when IPAP is equal to EPAP, that means basically it means that there is no pressure support given. Pressure support is 0. So when pressure support is 0, IPAP is equal to EPAP. Then we call it continuous positive airway pressure or CPAP. You understand? Basically it means giving PEEP without any pressure support. The patient is breathing spontaneously. That's called CPAP. Okay. I don't know whether I made it more confusing for you all, but basically it means giving PEEP without any pressure support. So when you give the pressure support is 0, IPAP is obviously equal to EPAP. Okay. That is, like I said, the patient is breathing continuously, otherwise the pressure is kept at 5 or whatever PEEP you have kept, and in between the patient is making spontaneous breaths. That is CPAP. So what are the drawbacks of pressure control ventilation? Basically, like I told you, with pressure control ventilation, depending on the compliance and the resistance of the lung, the tidal volumes can fluctuate. So you cannot guarantee a particular tidal volume, but if you use PRVC, you can get over this particular problem. But even in PRVC, the pressure goes up too high, then the ventilator will not deliver above the alarm that you have kept. And like I said, the minute ventilation is a mix of the peak pressure, the time, the lung, and test wall, so you may not get the fixed volume. The main problem in pressure control is that if you have to keep alarms properly, because sometimes the sudden change in the compliance resistance of the airways, the patient may not get the tidal volume that you desire. In fact, it might be a little dangerous. So you require a little more monitoring. In volume control, the main problem really is going to be that the pressures might go up. When you want to deliver a certain volume, the pressures might go up. So that's the main problem with volume control ventilation. And sometimes for the same, because you have a square flow pattern, the peak inspiratory pressures for the same tidal volume are much more than with pressure control ventilation. The peak inspiratory pressures, how much this contributes to barotrauma is debatable, but for the same tidal volume, the peak inspiratory pressures obviously are going to be much higher with volume control. The mean airway pressures actually some people say lower with pressure control ventilation as to deliver the same tidal volume. Okay, that's a disadvantage of volume control ventilation. And the other problem with volume control ventilation is that basically, generally what happens is that people, quite often what they do is that you find that you use volume control and the pressures are going up, then you change to pressure control. But what you should realize is that the lung is the same. The lung is not going to change. By changing the mode of ventilation, the lung doesn't change. So if you're going to, with volume control ventilation, you find the pressures are too high. With pressure control ventilation, you find the volumes are too low. So changing the mode of ventilation doesn't really help very much. That's a common mistake people make. Pressures are too high, change to volume control. Volume control, volumes are, so that doesn't matter because ultimately the lung is the same. The lung is still remaining either stiff or tumor resistant. Just merely changing the mode of ventilation not going to change anything very much. So if you know one mode of ventilation well, you can stick to that mode. You really don't have to keep changing modes. There's no study has shown that one particular mode is superior to the other mode for most situations. Okay? So you know to know a couple of modes well. And remember the same lung. By changing the mode of ventilation, you're not going to change the properties of the lung. That is something I have to remember. So just changing modes doesn't really help you anyway. Master one mode, see why it is not working, and try and improve the lung. Bronchodilation, pneumothorax, fluid, whatever. Changing the mode of ventilation is not really going to help you very much most of the times, okay? Generally, patient comfort generally is more comfortable, generally pressure control, pressure support mode, because initial patient, it is decelerating flow. I should have talked about this. Basically, what do you mean by decelerating flow? Basically means, in volume control, I told you the flow is constant because in pressure control, suppose once you get a pressure of 25, when the pressure starts, air will go on till the pressure reaches 25. At that time, the pressure in the mouth is 25, the alveolar pressure at the end of expiration is 0. So there's a big gradient between the alveolar pressure and the mouth pressure. So air goes in very quickly. As the alveoli start getting filled up, the pressure in the alveoli starts increasing. Now the gradient between the mouth and the alveoli starts reducing. and therefore the flow starts decreasing, the flow starts decelerating. And finally, when the pressure in the mouth is the same as alveolar pressure, the flow will stop. You understand? So if you ultimately the end alveolar pressure will be the same as the pressure that you set once the flow stops. You understand that? That is why flow is decelerating. But decelerating flow more or less matches our own inspiratory pattern, because initially when we breathe also we require a faster, flow of air. After that, we require slow flow. So square flow doesn't always match our own flow pattern. We don't have the same need of air throughout inspiration. So for most patients, pressure support ventilation is more comfortable than volume control ventilation. But unfortunately for most doctors, they're more comfortable with volume control ventilation. But ultimately, like I said, it doesn't matter. If you keep in volume control, you keep the flow rates high enough, you might be able to keep the patient comfortable, but you need to know your mode well and need to be comfortable with it. But quite often you might find in volume control, sometimes patients are not very comfortable. They are flow starved. Changing to pressure control sometimes makes them a little more comfortable, because the initial flow rates are much faster with flow control, with pressure control than with constant flow. And like I told you, this is why it is decelerating flow, because the gradient between the mouth and the alveoli starts reducing as more and more of the alveoli gets through. Okay. And the main thing also, other advantage of volume control mode is that you can do troubleshooting a little better with volume control. You can use peak inspiratory pressures and pause pressures, etc., and do troubleshooting. That, of course, we will talk to you about. With volume control, that facility is not available with pressure control mode. So maybe that point of view, sometimes you want to troubleshoot, you should at least temporarily change to volume control and look at the graphics and see for troubleshooting. Okay. And like I told you, SIMV, though very popular, this probably should not necessarily be used, and probably actually prolongs the entire weaning process. So probably not a big role for SIMV nowadays, though still extremely popular, but probably not really very useful. And by and large, each time you keep getting newer ventilators, a lot of fancy modes, etc., more expensive. But as you grow older and wiser, you realize you really don't need, like as you grow older, I've done away with more advanced hemodynamic monitoring. As I'm growing older, I'm doing away with most. I realize I can ventilate most patients with the very basic CMV pressure control ventilation. Really don't need any great ventilation. Of course, when you're young and you're dynamic, you want to learn all the more fancy things. As you grow older and wiser, you realize that simple is best. Keep it simple, keep it less complicated. But of course, we all go through that process so you'll have to know, you all are starting out in life, you all will need to know all the fancy modes, but as you grow older and wiser, 20 years from now, you also will maybe stick to good old pressure control, volume control, whatever. So when you're keeping a patient on a ventilator, basically, of course, the first thing you need to know is what mode to keep him on: volume control, pressure support, whatever. That's the mode that you select. Like I told you, by and large, it doesn't matter what mode you select. This should be the mode that you're most comfortable with. The patient lung is not going to change depending on what mode you've set. Okay, so it should be a mode that you're comfortable with. And remember, pressure support is not a weaning mode. Pressure support can be used as a initial mode of ventilation also in a patient who's spontaneously breathing. Obviously, in a patient who's under anesthesia, you can't use that. But in a patient who's spontaneously breathing, even pressure support is an initial, can be used. You should keep the rate that you need to set. Obviously, that depends upon lots of things. PCO2, asthma, ARDS are really not going to go on all that. You all know the concept of permissive hypercapnia. So rate, tidal volume and pressure setting. So depending on tidal volume, if it is flow controlled, what volume you want, and pressure, if it is pressure controlled, you obviously can't adjust pressure, tidal volume, but you use the pressure which will deliver the volume that you want. Okay. Inspiratory flow, IE ratio, PEEP, FiO2, and inspiratory trigger. So I talked to you about the decelerating flow and the square flow. Square flow is more for volume control ventilation. Decelerating flow is more for pressure control type of ventilation. But in PRVC, you have volume control with a decelerating flow. Okay. The tidal volume is the same in all three patterns, but like I told you already, decelerating flow is the initial. So quite often the patient decelerating flow, the patient is less likely to get flow starved. Okay. Some people say, that the problem is volume control ventilation. Some people feel that volume control ventilation causes more unequal distribution of alveoli, especially the conditions like ARDs, etc. Because when you give a volume of 500, all the tidal volume might go into the alveoli which are most compliant. So there will be over distension of the compliant alveoli, and the less compliant alveoli will not get any air at all. So a lot of people think theoretically volume control ventilation can cause less, inequitable distribution of air. Whereas in pressure control ventilation, once an alveoli gets filled and the pressure reaches a certain level, no more air will enter that alveoli. Then the other air has to enter the alveoli, which are so-called longer time, gradients. That because they're subject to the same pressure for a longer time. So they feel pressure control ventilation causes more equitable distribution of ventilation. So theoretically, Pressure control is better to cause a more uniform distribution of ventilation. Volume control probably causes less uniform distribution of ventilation. So theoretically, pressure control ventilation is better for ARDS, but no study has shown that this mode of ventilation is superior to volume control ventilation, which is why a lot of people use PRVC in ARDS, because the mode of ventilation is decelerating the pressure control type, but you can control the tidal volume, which is why a lot of people use PRVC in ARDS, provided the patient is sedated and comfortable. Okay, like I told you, PRVC may not be very successful if the patient's mode of ventilation keeps changing, but in a patient who is breathing reasonably constantly well under good sedation, PRVC achieves the best of both worlds. You're making sure you're getting a desired tidal volume, low tidal volume, whatever you want, at the lowest pressure in a decelerating mode, which might cause a more equitable distribution of ventilation, which is the whole theory behind PRVC for ARDS. Okay. IE ratio, like I told you, usually set to 1:2, but remember, you keep it 1:2 because normally in inspiration also, that is what our usual IE ratio is when you are breathing spontaneously. Inspiration takes 1/3 of time, expiration takes 2/3 of time. But like I told you, when you're doing IE ratio, remember that IE ratio is constant only if the patient's rate is equal to the rate that you have set. Once the patient rates increases much more than that, then inspiratory time remains constant, but expiratory time keeps getting shortened. And progressively expiratory time gets shortened. Quite often patients have auto PEEP. So quite often I've noticed that respiratory technicians or register keeps a rate of 15 and they keep an I ratio 1:2. So the patient gets, inspiration. So when you keep in a rate of 15 and I ratio 1:2, actually what you are seeing, each breath is 4 seconds. And if out of that, if the inspiratory time is about 1.2, 1.3, expiratory time is going to be 3.6 or something like that. That is if the patient is breathing 15 times a minute. But quite often the patient starts breathing at 25, 30 times a minute. And nobody changes the I ratio, nobody changes the rate. The patient still gets, now he gets only 2 seconds per breath, out of which 1.2 seconds is inspiration. He gets very little time for expiration. That's why he gets auto PEEP, hypotension. It happens all the time. So what I say is, if you're going to keep a rate, you can't keep setting I rate. Try and match the patient's own rate. Keep a rate which is about 2 or 3 seconds less than his own rate. 3 or 3 breaths less than his own rate, such that he triggers. Because if you keep a rate too fast, the patient won't be triggering at all. The patient only, you don't want him not to trigger. But don't keep a rate too slow, because then the I ratios keep changing. And then they get auto PEEP, etc. So better to keep a rate which is closer to his rate. Generally, it is better to keep expiratory time much longer. Inspiratory time. So always when you are setting in your mind, don't look at IE ratio, don't look at anything else. Look at what is the inspiratory time that you're keeping for the patient. Fortunately, most new ventilators now give the inspiratory time, so you can calculate. And generally, 0.8 to 1.2 seconds of inspiration is the ideal for most patients. If the patients have problems like COPD, asthma, etc., maybe it's better to keep inspiratory time shorter. If the patients have conditions like ARDS and all, maybe you can keep it slightly longer. But the main thing is that there should be no auto PEEP. You understand? Because otherwise that can cause more other problem with triggering, problem with hypotension. So remember, don't look at IE ratios, etc. IE ratio, flow time, etc. Ways are ultimately adjusting inspiratory time. That's what you should look at. Like I said, fortunately, most new ventilators give you inspiratory time, but if you don't have that, in your mind, calculate what inspiratory time are you setting and set that. Don't worry about the rest. Flow time, IE ratio, etc. Just a way of ultimately adjusting inspiratory time. Okay. So this, but like I said, if you keep it longer inspiratory time, maybe it will help in ARDS. Shorter inspiratory times will help you in obstructive airway diseases. So same thing. Peak flow is ultimately another way of adjusting inspiratory time. You keep a peak flow faster, the tidal volume is going to deliver in a shorter time. Inspiratory time is going to be shorter, but at the expense of higher pressures. If you give peak flows too slow, inspiratory time is prolonged, pressures will be lower. So you have to balance the inspiratory time with the pressure. So it's all a balance that you set. You can use the highest peak flow that you can achieve at the same time without too dangerous a pressure. That is the whole idea. But ultimately, again, what you are adjusting really is inspiratory time. That is what you are doing. And also you're trying to adjust some amount of patient comfort. If you keep too low peak flow, the patient may not be very comfortable. But at the same time, if you keep too high a peak flow, the patient may be more comfortable, but the pressures may go up. So you need to have some balance. And sometimes you might have some mild sedation as well. Okay. So that's, like I said, if the peak flow is faster, inspiratory time is shorter. Peak flow is slow, inspiratory time is slower. IE ratio becomes, much shorter. This I already talked about. So as the rate goes up, what happens is inspiratory time remains constant. Again, very important. People don't realize that. What happens when you increase inspiratory? Expiratory time is what is getting shorter. Inspiratory time, like systole and diastole, when the heart rate goes up, systole remains the same. It's only diastolic time that gets shortened. So you get diastolic dysfunction. Similarly, when on the ventilator, when the rate goes up, inspiration remains the same, expiration shortens, and then you get auto PEEP, which is something similar to your diastolic heart failure. So that's the whole problem. So always look at inspiratory time. Look at whenever you're calculate, this is the inspiratory time I've set. So that means now the patient is going to get only so much time for expiration. Quite often we're leaving too little time for expiration by not changing the inspiratory time, not shortening the inspiratory time in patients who have higher heart rate, higher respiratory rates. And that's what causes the hemodynamic instability, auto PEEP, etc. Then, of course, we have the trigger. Like I said, what trigger essentially is, what is it that gives a ventilator signal that it should start a ventilator breath? Please let me know if you have finished or what time. I don't know. 5 minutes. Okay, that's why. So basically, there will be time triggered, pressure or flow triggered. So time, basically, like I told you, time essentially is in controlled ventilation, or generally that's in controlled ventilation, because if you give a rate of 12 every 5 seconds, automatically the ventilator delivers the breath. That's essentially in controlled ventilation. But otherwise, in patient triggered ventilators could be either pressure triggered or flow triggered. So basically, the important thing is to keep the trigger sensitivity, because it should be sensitive enough such that the patient makes a minimal effort to trigger the ventilator. The patient should make some effort, but not so much effort that he gets tired and fatigued and delays whole weaning process. So he should be sensitive enough such that he triggers the ventilator. So quite often people keep pressure of -10, -15, but that is not good, because generally the patient do that means much more work to trigger the ventilator. So it will be sensitive enough, at the same time not so sensitive that he gets a phenomenon known as auto triggering. That's the main thing. So generally, pressure triggering, therefore in pressure triggering, generally the trigger is kept at -1 or to -2. -2 is generally optimum. If you keep more than -2, -3, the patient has to do much more work to trigger the ventilator. So pressure triggering basically, remember, it is a trigger below PEEP. It is not absolute. When you say -2, it is below PEEP. So suppose the PEEP is 10, you have to just make the pressure down to 8. So it is pressure below PEEP, not the absolute pressure. So when you say trigger -2, the patient just has to generate a pressure of -2 to trigger the ventilator. If you keep it too much, the patient will do much more work, but you keep it very low. Even things like water in the circuit, the heartbeats and etc. can trigger the ventilator, and you have a phenomenon known as auto triggering. But sometimes you are called to see the patient and the nurse tells you the patient is breathing 50 times a minute, but the patient looks comfortable. You ask him, he says, I'm fine, nothing else is happening, but he's breathing 40 times a minute. That's the time it's probably that your trigger is kept too sensitive and it is auto triggering. Something in the circuit, some heartbeat, something else is triggering the ventilator. So then the thing is just to increase the sensitivity from -1 to -2 or -3, and you can prevent this auto triggering. So that's the main thing. Not too sensitive, not too insensitive. That should be pressure triggering. Then you have flow triggering. Flow triggering is theoretically supposed to be more sensitive than pressure triggering. In flow triggering, what happens is something called a flow by circuit. There is air continuously keeps flowing from the inspiratory limb to the expiratory limb. Therefore, the moment the patient needs some air, he doesn't have to open up the inspiratory valve. He just gets air straight away, because there's air already flowing from the expiratory limb. And the ventilator calculates if there's any difference between the air delivered to the inspiratory limb and the air coming out of the expiratory limb. The moment the patient makes an effort, there's going to be a difference, because the amount of air going to the expiratory limb is less than the air gone through the inspiratory limb. The ventilator therefore knows that the patient has made an effort and will deliver the entire tidal volume that has been required. So flow triggering theoretically was supposed to be more sensitive and supposed to deliver air faster than pressure triggering. But with most of the modern ventilators, the pressure trigger is also very sensitive, so it doesn't matter whether you use pressure or flow. Theoretically, flow was more sensitive, but with modern ventilators, probably doesn't matter whatever you use. The main thing is make sure they're not too insensitive, nor are they too sensitive. This should be optimal. PEEP, you all know about PEEP, and I'm sure you'll be talked about how to ventilate. Basically, it's like a balloon, we all know that, to initially when you're opening up a balloon, it takes some time. But once certain amount of air has, filled the balloon, then it becomes much more easy to, blow the balloon. So PEEP just does that. It increases the initial functional residual capacity so that the compliance of the lung improves. That's the main thing with PEEP. Okay, so it moves the lung tidal volume to the more compliant area of the pressure volume curve. And you should know a bit about PEEP versus auto PEEP. In PEEP, the same pressure is transferred from the mouthpiece to the airways, whereas in auto PEEP, at the mouthpiece, the airways still the pressure is 0. But essentially because of air trapping, because of not enough time for expiration, only the alveolar pressure has gone up. That is auto PEEP. In PEEP, what you have said, the PEEP is the pressure is the same throughout the entire airways. So this is the initial settings on a patient with, on a ventilator. I'm sure you'll be talked about in the afternoons. I really won't go into great details for all that. The main thing is, of course, again, troubleshooting we'll talk to you about. The main thing initially troubleshooting is to disconnect the ventilator, bag the patient. That's the first thing. The safety first, disconnect and bag. Because when you're bagging also, you can find out some bit about the compliance and resistance of the lung. First, that's the safest thing. Disconnect and bag. Then start doing the troubleshooting. This will be talked to you in the afternoon. I really won't talk to you much about this, because basically it's about how about looking graphics and troubleshooting whether the problem is with compliance of the airways or with resistance of the airways. A very famous chart, and I'm sure you'll be talked about in the afternoon, how to separate problems with compliance versus problems with resistance. So therefore, basically, remember there's no ideal mode of ventilation, whether it's pressure control, volume control, pressure support, there's no ideal mode. Changing from one mode to the other by and large doesn't do any difference because the lung is not going to change. Everybody always do that, change from one mode, it doesn't matter because the lung is not changing. Unless you change your lung, the ventilator mode is changing, the ventilator mode is not going to help. Tackle the lung, not the ventilator mode. Use the mode that you're most comfortable with. That's the most important lesson. Master one or two modes and use those modes. Most of the time, they will work. There may be very, very few exceptions. Most of the time, master one or two simple modes is enough to handle more than 99% of your patients. So I hope I made it as simple as possible. Thank you.
It amazes me every time I come and listen to Sir. I always learn so much more. I might listen to you more than my parents, I feel. You're Sir, amazing, sir. Everything that you do is perfect for me. So knowing a lot of things is great, but knowing what to use where is brilliance. I think I get the point through. Knowing a lot of things is great, but knowing what to use where, how to dissect the evidence and go ahead and understand what to use where is brilliance. And no one better than Dr. Rahul Pandit to take that topic on evidence and how, which is the best evidence available in mechanical ventilation. And before we get into the topic, I'd like to felicitate Dr. Rahul Pandit for having spent his time to come all over from Fortis, of a busy hospital like Fortis Mulund, to help us understand about the evidences in mechanical ventilation. So Dr. Ambadikar, would you please felicitate Dr. Rahul Pandit? And Dr. Rahul Pandit has been a teacher, senior colleague of mine, and we've had a lot of time together. Good times. The next person that I'd like to call in is another friend of mine, Dr. Nitin Rathod, one of the biggest practices in Bombay, and possibly a very senior teacher, DNB teacher, and a critical care consultant, Dr. Nitin Rathod. Dr. Ambadikar, would you please felicitate Dr. Nitin Rathod, please? We would possibly all agree about Dr. Rishi Kumar. Rishi Kumar is like the backbone of Hinduja, I feel. Isn't it? Dr. Dr. Rishi Kumar is like the backbone of Hinduja and possibly does almost everything at Hinduja. He is a fantastic teacher, orator, and thank you, Rishi, for coming and helping the students to learn. I would call upon Dr. Asit Degre to please felicitate Dr. Rishi Kumar. Another senior colleague of mine, Dr. Chandrasekhar. What can we tell about him? He makes things so simple. It's great to listen to Dr. Chandrasekhar, and he tries to convey the point. Don't miss him out on the stations and graphics, and see that you learn everything that you can from Dr. Chandrasekhar. Sir, thank you very much for coming for the workshop. Dr. Rahul Pandit, would you please felicitate Dr. Chandrasekhar? Dr. Akshay Chalani, I don't know where he is. Smart. So, Dr. Akshay Chalani is always before time generally. Today is the first day he's been because he's been busy with some patients over there. And a great pulmonologist and critical care consultant. Dr. Ambadikar, could you please felicitate Dr. Akshay Chalani? I don't know how many of you all know Dr. Mehul Shah. Dr. Mehul Shah is just like Dr. Pandit, trained in Australia, and fantastic orator, now presently working as a critical care consultant at HN Hospital. Is Dr. Mehul Shah around? Dr. Mehul Shah? Not around. Okay. So let's call upon the next speaker, Dr. Bharat Jagyasi, a friend of mine, part of the executive committee of the Indian Society of Critical Care Medicine. Gaurav, can you call Dr. Bharat Jagyasi, please? Dr. Bharat Jagyasi? Oh, there's Dr. Mehul Shah. Dr. Mehul Shah from HN Hospital, and catch him at the station of graphics again, and do learn whatever you can from Dr. Mehul. He's a phantom on that. All right, Dr. Mehul Shah. Dr. Bharat, is he around? So let's see. We have another dashing critical care consultant, Dr. Bharat Jagyasi, and now presently heads. Can I reveal it to everyone? Yeah, he heads Terna Hospital as of now, Terna Medical College, critical care, and I think today is the second day. Is it? It's very nice to see a person, on the second day of duty coming over here. I hope your CEO knows about this. Yeah. All right. So Dr. Bharat Jagyasi, Dr. Rahul Pandit, could you please felicitate Dr. Bharat Jagyasi, please? All right. So, as I talked, what should be the? There's a lot of data all around the place. Lot of data. You open up Google and you'll possibly see 100 data on each and every subject. Now, to understand what to use from there, I would call upon Dr. Rahul Pandit. I myself call him every time when I'm in intensive care and I need to know the evidence in the right way, and that is the reason I refer to him when we have certain problems in the ICU. Dr. Rahul Pandit, I'd like to. I'll just slow down your PPT till that time.
डॉक्टर हेगड़े का तो नहीं रहा, ये जो यूएसबी है सर का तो नहीं,
स्लाइड चेंजर है।
फ्लाइट चेंजर। Thank you very much, Sanjeet, for the kind introduction, for organizing this fantastic workshop. You've got more than 120 registrations. Congrats for that as well. It's a pleasure indeed, and luckily, Hegde sir has done my job very, very easy. Because if you remember his second last slide, there is really very little evidence in terms of mechanical ventilation if you look at the modes. Okay, so there is very little evidence as to what mode you should be using. But it is important to know what is evidence. What are we looking at in terms of evidence? So if you look at this little pyramid here, we have, it doesn't work anyways, we have the systematic reviews, randomized controlled trials at the top. And then as we go down, we have multi-center, single-center trials, cohort studies, case studies, case mix. So the evidence sort of goes from the top of the cone of the pyramid down to the base of the pyramid. And what we are really wanting to know is what is on the top of the pyramid. Okay. Unfortunately, most of the data which we talk about comes from the bottom of the pyramid. Okay, so there are very few studies which actually talk about evidence-based medicine in terms of mechanical ventilation. But mechanical ventilation bundle as such, the whole process, the whole paraphernalia which goes along with the ventilation, there is scattered evidence here and there. Okay, so we will look at all of those things in toto as to what are the different things which are talking about evidence in terms of mechanical ventilation as a bundle, not just putting a patient on a ventilator and working on that. So not just modes of ventilation, not just triggers of ventilation, because that has been already covered by Dr. Hegde. And if you know, there was particularly no different mode which we actually should be using or should not be using. Okay, so what do we actually know? We know a few things about the best practice guidelines right now. We also know a few things about sedation and paralysis in mechanical ventilation, to assist mechanical ventilation rather. A little bit of modes, weaning process, and ways to sort of prevent ventilator associated pneumonia. And then you have your non-invasive ventilation where the evidence is there as well. So we are going to look purely into what is the current evidence. I'm not going to go into opinionated medicine. I'm going to basically talk about what is currently there in the literature which supports our practices. And what I'm not talking about has got very little evidence in the literature, or perhaps just case studies which have been done. Okay. So currently, the only ventilatory strategy which has shown to improve mortality is the protective lung ventilation in ARDS. It is rather a problem that protective lung ventilation has creeped into our day-to-day practice in such a way that even if the patient doesn't have ARDS, just normal ventilated patient, just a patient who's come post-operatively, there is a immediate reaction from people that let's just give a very low tidal volume ventilation. You really don't need to do that. But that's how the protective lung strategy has been bombarded to everybody, that you need to protect the lungs, you need to protect the lungs. Not really necessary, because the evidence is only in ARDS. Yes, the motto behind doing that for everyone is not to do any further harm to the patient, but it's not really necessary. The evidence-based practice would just talk to you about ARDS. Okay, all modes have a potential to harm. It is not the mode which you use makes the difference, but it's the intensivist, the person at the bedside, how intelligently he's going to use that mode is what makes the difference. And there was no other person better than Dr. Hegde who sort of alluded that in the talk previously. So where does the evidence for protective lung ventilation come from? This comes from the landmark study which was published in New England Journal of Medicine under the ARDSNet trial, where they compared for randomized control trial. So they compared two different modes of ventilation, two different modes of tidal volume, 6 ml per kilo versus 12 ml per kilo for the predicted body weight. It was also decided beforehand that the plotter pressures would be kept at around 30 or less. The ventilator settings were standardized, oxygenation targets were put, and available combination of FiO2 and PEEP were sort of done. And it was not surprising that if you look at this Kaplan-Meier curve here, the one with the bold red is your survival. So if you were having a low tidal volume ventilation, the chances of survival were very, very high. Okay. So the study, in fact, was stopped after the fourth interim analysis. It was sort of going to recruit double the number of patients. It was stopped at the fourth interim analysis because there was a significant difference in mortality already, and the safety committee of the study decided that it would be unsafe to actually let this study continue any further, because there was a clear picture emerging that the protective lung strategy was working, and it was working in favor of the patients who were getting a protective lung ventilation. So the problem was that they were not willing to subject any further patients to be randomized in the 12 ml per kilo arm, so that we would be causing any harm to them. So basically a very, very high level evidence where the study proved beyond doubt, and you can see that in our day-to-day practice that it's become much easier now with the protective lung ventilation to ventilate ARDS patients quite effectively. Okay, and this was the numbers. So with the low tidal volume, the mortality or the death before discharge to home was 31 versus 39.8%. So almost a 10% absolute difference in the mortality. Okay. The number of ventilator days, the breathing without assistance, and all of those things did not make a big difference. However, it did make a difference in terms of mortality, which was the primary objective of the study. The second evidence comes up again with patients who are having oxygenation failure or ARDS, which is prone ventilation. Okay. So prone ventilation is the second best evidence which we have currently for mechanical ventilation, and not really the ventilator associated thing, anything which I'm talking about. It is a patient associated thing. So what happens when you have a ventral patient, when you have a patient who is lying on his back, you have majority of your lung which is at the back of your body, and it obviously gets wet. It obviously has a lot of gravity induced problems, and you can see that when the patient has got this prone position done, the dorsal becomes ventral and the ventral becomes dorsal, or the pulling of the saliva secretions just go out. You are able to suction the patient out. The oxygenation is better because the lung is at your back. sort of the lung opens up, recruitment becomes easier, and those who work with most of the units now in tertiary care, I'm sure would be aware that we prone the patients very, very quickly now. We actually don't wait for the complications to arise, especially with Fortis where we are working. I mean, there are a couple of points from my unit here. The first instance of hypoxemia, if you're not able to control, we flip the patient. Okay. And how does it help? It increases the FRC. It sort of helps in the blood flow redistribution. It obviously changes the diaphragmatic movement and improves the suction removal. Now, is there a study which actually proved it? Yes, in 2015, there was this trial which was the PROSEVA trial, again published in New England Journal of Medicine, which recruited close to 475 patients. Each group had around 230 patients odd. They were equally matched. The only changing mantra of this study was they were proning patients for a long time. Average proning was for 17 hours. Okay. So previously there were at least 4 or 5 big studies where proning was practiced. Unfortunately, the proning studies did not show a mortality benefit. The reason was the proning was not done for longer periods. And now with this one study where we are doing proning for at least 17 hours a day, it made a big difference. Again, you can see this Kaplan-Meier curve here. The prone group did exceptionally well. And you had a less mortality at the end of 90 days in the patients who were prone with a p-value which was very, very significant. So these are the 2 trials which basically have excellent evidence, level 1 evidence. We should be practicing them in our current era of mechanical ventilation. Anything after this which I am saying does not have this strong an evidence. Okay, so this is the best evidence which is there currently for us to see, and anything after that, the evidence is going to go slowly down towards the base of the pyramid until the point where we come up to some cohort studies and some emerging evidence out of that. Sedation and paralysis practices. Okay, now why did I term it in the strategies to reduce VAP? Obviously, anything which you do which will help the patient to wean off the ventilator very quickly will actually reduce your incidence of VAP. Okay, so your sedation and paralysis practices matters a lot. Though it matters for effective mechanical ventilation as well, it also matters to the point that he may eventually help you in weaning the patient off the ventilator. Okay, so one of the studies which have been done extensively, and I'm sort of going to put up a randomized control studies meta-analysis, is the daily interruption of sedation in ventilated patients with mechanical ventilation in intensive care unit. Okay. Now this is a busy slide, but what it effectively shows is on the left side of the forest plot here, the one which is there. Let's see if I can. No pointer or anything. A green pointer. Yeah, it doesn't come up. Yeah. Okay, doesn't matter. So if you look on the left one favors the daily sedation interruption. I'm talking about left on this side. Okay. So left favors daily sedation interruption. The right obviously favors the traditional practice of not interrupting sedation every day. And here you can see that there are 5 studies, and all of these 5 studies basically had a mean time of around 4 to 5 hours of sedation being interrupted every day. And you can see that there was a difference in the duration of mechanical ventilation in days by just by one parameter being changed, which was interrupt the patient's sedation every single day, allow a awakening trial every single day, see and assess for weaning every single day, and then if required resedate the patient. Okay. The same study also looked at few other things. It looked at the length of stay in intensive care, again significantly different. Length of stay in intensive care in patients who had sedation interruption was significantly lower. The third one was unplanned extubation. Why do you need to look at this? If you are going to interrupt the ventilation every single day, there has to be a fear in your mind that the patient might actually self-extubate, or the patient might, have a dislodgement of the tube because he was thrashing around, and all of those things. So it is very important parameter to see whether there was any difference in the rate of unplanned extubations. Fortunately, there was none. Okay, fortunately there was none. Even if you interrupted the patient's sedation every day, the vigilance was there in such a way that it did not lead to unplanned extubations at a higher rate. Okay, and then the last and not the least is how many of these patients went on to have a tracheostomy. We all work in ICU. We all know that the more heavier the sedation the patient needs for effective mechanical ventilation, we start thinking in our minds that he's going to need a tracheostomy. And I would like to have a show of hands. How many times have you done a tracheostomy and the next day patient looks like he probably didn't need it? He just comes off the ventilator very quickly, right? Most of us have gone through this, and probably the genesis of this is that we were over sedating these patients, and we were not actually interrupting their sedation adequately enough for whatever reason. I mean, the reason could be ongoing hypoxia, reason could be agitation, but all of us have that feeling that we've done a tracheostomy yesterday and today the patient looks so nice, so good. What you did was you had a conference amongst yourself and your team, which includes the nursing staff, to effectively stop the sedation once the tracheostomy was done. And that's the only difference which you've made. Do you really think by changing over from a endotracheal tube to a tracheostomy, by decreasing the dead space ventilation by say 40-50 mils, would you make that big a difference in the patient? Probably not. Okay, so some patients definitely are over sedated in our intensive care unit, and we could change that by interrupting the sedation every single day. The next thing which is evidence-based is spontaneous breathing trials. Okay, so spontaneous breathing trial again goes hand in hand with daily interruption of sedation. So that's why it needs to be combined together. If you're going to give a spontaneous breathing trial to assess the patient's readiness for extubation or separation from a ventilator, you need that patient to be separated out from the sedation before you do that. Okay, so spontaneous breathing trial. This was one of the studies which was published long ago. Okay, but it was done in a coronary care unit, 300 patients, randomized controlled, basically looking at rapid shallow breathing index followed and versus a spontaneous breathing trial. Each arm had around 150 patients in it, and the physicians were notified when the patients had successfully completed a trial of spontaneous breathing to be assessed for extubation or not. Okay, so if the patient would pass the spontaneous breathing trial on his own, he would then be thought of separating from the ventilator, otherwise not. What were the outcomes of these studies? The outcome of this study was there was almost a 1.5 day reduction in mechanical ventilation. So we just heard from Dr. Hegde again, and I'm going back to him, that SIMV is a poor mode for weaning or ventilating, okay? Because you're allowing the patient to actually work harder. And all of us, from my generation at least, I have grown up using SIMV mode because we were taught that mode. I'm basically an anesthetist. I mean, I was taught that mode to use in theaters, and then I sort of carried forward that mode for a few years in intensive care before I realized that mode has become obsolete. It's really not necessary to use SIMV. And similarly, pressure support ventilation, Cpap ventilation, all of those things have slowly come up to a point now that we would now want to give them a spontaneous breathing trial, perhaps even go further and go a TP's trial. And TP's trial is now what has become a standard of care. So once you go on from a spontaneous breathing to a TP's and you do a TP's trial for say 30 minutes to 120 minutes, longer than that is maximum of 2 hours, longer than that has no evidence. Okay, you are just torturing the patient if you keep the patient more than 2 hours. For me, if the patient tolerates a test for 30 minutes, it is good enough. Okay, so the evidence is for spontaneous breathing trials, almost a day's reduction in ICU stay, total cost, reduce incidence of reintubation, no question about it that we should be starting with spontaneous breathing trials and extubating our patients with TP's trials if limited. However, there are some limitations. Okay, not all patients would tolerate this. I mean, especially the COPD patients, especially the patients in whom the lung capacities are not very good. If you start giving them TP's trials, you are actually asking them to breathe through a small straw, which they are not used to. COPD patient uses all the resources it has. It tries to sort of pucker the lips so that you can have air sucked in. The nasal flaring happens so that whatever amount of air can be sucked in is sucked in. So they have a different type of a ventilatory requirement. So in them, and I'm going to cover that up,